showing up. I know all things will shut down in a couple of hours. But I'm very glad today that we have Ethan here from Data Plus team in the summer. He's done, he and his team has done lots of interesting work in helping this project getting started. So they've delved deep into several problems and got very impressive results. So today I've asked him to, on behalf of the team, share his experience and also some results with us. So we can then take over the baton and figure out where to go from here. So we'll start with your presentation, and maybe for those of you who have maybe had a chance to check out some of the documents we scattered around in a shared folder, this is your opportunity to ask questions. Okay, so, oh, and also I think as a matter of logistics, it will be nice for one of our grad students to serve as the scribe for the meetings to document what's talked about here. Right. I do not see Yu Hao here, so, so you will have to do it. And you have access to the folder, right?
Yes, I do.
Yeah.
Do
so
you have like specific folder in there?
Yeah, there is like a meeting notes thingy. Was it like 2018 meeting notes?
Yeah.
Yeah, you can just start sort of appending there.
All right.
Yeah, great. Okay, so without further ado, I'll give you Ethan. There's Ethan here. And Ethan will actually do the presentation over his laptop. So we'll share his screen here. All right. There you go.
Hello, everyone. I'm Ethan. I work with Lucas and Caroline over the summer. And these slides are taken from a couple of presentations we had to give for Data Plus. But I took out some of them. Okay. So basically, the project outline, we sort of split it into two parts. First, we want to take sentences from a variety of sources: microphone audio, YouTube videos, and live shows like CNN, Fox. And then we want to find related fact checks from a database of previous fact checks. And specifically from the Share the Facts database. I don't know if you guys have looked at it at all, but these are some examples of sentences in this database. There are a little bit over 6,000 sentences which are political and in English. And that grows, so if someone from the Washington Post publishes a fact check, it gets added straight to this database. So then, just a walkthrough from Trump's State of the Union. One of the sentences he said was, "Since the election, we've created 2.4 million new jobs." And a sentence in our database from the Washington Post, from one of their fact checks, there have been about 1.8 million jobs created since January 2017, according to the Bureau of Labor Statistics. So our goal is to first go from the audio to this sentence, and then from this sentence to the relevant fact check. So the first step of that is audio to text. So in this case, since the State of the Union happened a while ago, this is using the YouTube video from the CNN coverage, I believe. But we can go from any of these audio sources. And essentially, this just involves a call to Google's Cloud Speech API. It's a little bit more complicated than that. It takes a little bit of audio conversion into a format that Google will accept. But most of the work is happening through Google. And as an example, with Trump's State of the Union, we can see that around 75% of the transcription sentences are transcribed perfectly. About 15% are near perfect, and around 10% are unusable. And this is based on Trump's State of the Union. But for example, if it's Trump talking in front of Air Force One with like loud helicopter noises in the background, obviously it's going to be significantly worse. And also microphone audio tends to be a little bit worse. So but anyway, step one is going from the audio to the sentence. Since the election, we've created 2.4 million new jobs. And then the second step is claim filtering. Again, we use an API for this. This time it's called the Claim Buster API. It was developed at University of Texas.
Arlington.
Arlington, thank you. And it's really good. What it does is it tells you how essentially fact-checkable a sentence is. So here we have 4 examples from the State of the Union. So for example, thank you is given a score of 0.15. This is what Americans have always stood for, is given 0.23. And both of these sentences, we can't really fact check. Even the sentence like Americans have always stood for patriotism, that's not something we can really fact check. Where we also doubled the child tax credit is something we can fact check. Because maybe they tripled it, maybe they didn't change it at all. And then the sentence we care about for this example, since the election, we've created 2.4 million new jobs, that is 0.73. And this is a histogram of all the sentences from the State of the Union. And empirically, looking at a variety of tax sources, we use a threshold of 0.25, which you can see on the graph. And so any sentence that we get from our speech-to-text transcription that has a score less than 0.25 from ClaimBuster, we throw out, and we don't even look for a fact check. And this is to make things faster. So if we're checking thank you 12 times, that's going to slow everything down. And there's also always the chance of a false positive. So if we can filter out sentences before we do actual claim matching, that saves us both time and increases our accuracy. So now, step 3 and the rest of the presentation essentially are all on this claim matching step, which is where we spent most of our time over the summer and is hardest part in the room and the space where there's probably room for most improvement. So initially, our problem statement was given 2 sentences, X and Y, one of which is a spoken sentence and one of which is a sentence in the Share the Facts data set. We want to check if they're paraphrases. So someone assuming sentence X to be true would infer that Y must be true, and vice versa. So our initial attempts, and these attempts are still in the GitLab repository, and you can still use them. So first, well, these were sort of developed in parallel, but the first approach is a long short-term memory neural network. And to do this, we used Google's news word embeddings. So sort of the first difficult part about this is that we're given text in sentences and English words, and we somehow need to convert that to numbers so that we can do some sort of machine learning. And so a common way to do that is with word embeddings. Google News word embeddings is among the most famous. There's also Glove and a few others. And so what we end up with is each sentence is represented by a 300 column by 50 row matrix, where each row represents one word. And if it's shorter than 50 words, we pad it with all zeros. And if it's longer than that, we truncate it. But very few sentences are. And then each word is represented by a length 300 embedding. And so these embeddings capture sort of semantic meaning, hopefully. And then the second approach is a more traditional, going back to that approach. And then finally, once we have these embeddings, we use a long short-term memory neural network, which is a neural network which tries to solve the problem of their complicated dependencies in English. So if I use the word it at the end of a sentence, it's referring to a word somewhere earlier in the sentence. So we need to somehow be able to sort of remember the earlier words, and that's what an LSTM attempts to do.
So for both of these approaches, they're still both framed as supervised learning problems.
Correct.
Right. So you have also some training data with basically correct labels where you say this pair of sentences is a paraphrase of one another.
Yes.
And you have some negative examples.
Yes. And those examples, initially, we sent out a survey to all the Data Plus people and a bunch of other people. But we didn't design it well enough. So it was like way too easy, and we got something like 99% accuracy. And so then we ourselves created harder examples. And that data set is in the repository. Yes. Yeah.
So for input for a neural network, is it 2 sentences?
Yes, it is 2 sentences. Essentially what happens is you have like 2 separate parts of the neural network, one for each sentence, and then you combine the results from each to get your final result. But yeah, good question. Then The second approach was a more traditional natural language processing approach. So we used part-of-speech tagging and word pair similarity, and we used a support vector machine for classification. And going a little bit more into a little more depth with that one. Essentially what we do is we first separate by part of speech. So we have one sentence here on the left after we take out stop words, words like the and, which aren't really relevant to the meaning of the sentence. And on the top, we have the fact check that we want to be matching with. So first we separate by words, by part of speech. And then for each word, for each part of speech, so first looking at nouns, we take whichever one has fewer words. So in this case, it's election and jobs compared to the 5 for the other sentence. And then we go along and find which word it matches best with. So in this Excel spreadsheet it's called the Wu-Palmer similarity score. Again, we use like built-in Python, or not built-in, we use Python functionality to get these scores. We didn't do it by hand. And so for election, the most similar word is statistics, and for jobs is in there. So that's a score of 1. So we take these two numbers, you can see it in the maximum column, and then we weight it based on how common these words are. And then we use that to get sort of like a noun score, a verb score, an adjective score, and an adverb score.
So here, by how common a particular word is this with respect to your text corpus, or is it with respect to some kind of other like building Python?
This is with respect to a corpus of political speeches.
Got it.
So you can see actually how common these words are at the top. I believe higher numbers means less common.
Okay.
Yes, less common.
Right.
And so, for example, have is only a 2.1, whereas election is a 6.3. And we wanted to use a political corpus because there are words in politics that aren't used that much outside of politics, but are very common in politics.
Yeah, so you give more weights if it's more common.
If it's less common.
Oh, yes. Yeah.
What happens if like there are 2 words in the
Say that again.
what happens if there are two words in the corpus that are like opposite to each other? Do you just extract them before you do this kind of thing?
Well, I'm sorry, I'm not sure that I'm understanding your question.
So, for example, you have a pair of words which are opposite to each other. I cannot think of an example right now, but maybe like the rate of getting a job and the rate of like losing a job.
Okay, sure.
So like what happens between them? So when you compute the score, is it like positive or negative, or do you just pre-perceive it?
So the similarity score will be very similar for those words because it's based on how they're used more than their exact meanings. So for example, like red and blue have very high similarity scores because they're used in the same context. But in word embeddings, then it's possible that those vectors would be opposite or something. But in this case, they're going to be very similar.
Right.
Does that answer your question? Sorry. Okay, perfect.
I think, so like in your case, like have or have not, the not will likely be filtered out.
Yes,
Like,
it will.
So yeah, in that case, it wouldn't really catch that.
Another just sort of a worst case example would be high and low, right?
Yeah.
Whether you match them or not. And one would argue that you should match them because if you're not, there's a way to paraphrase one into another. So
Yeah, and those will get a very high score here. Okay. So,
so on this part,
yeah.
So this module where you were measure the word similarity, that you could also just replace instead of this one based on co-occurrences or word net with word embedding and just compute cosine similarity, for example.
Yes,
here.
that is true.
Is that does that show any difference? Like how sensitive is this method to that particular tweak?
to how we're calculating these
Yeah, how the
similarity
word
scores?
similarity is.
We didn't actually look at that much. That'd be interesting to look at. But it seems possible that the LSTM neural network should be able to achieve similar behavior if that's better.
I see.
Yeah. Okay, so I don't want to, this is all I sort of have to say about these two approaches because our final approach isn't very related to either of these. But these models are still in the repository. You can still use them, so I don't want to touch on them more. Okay. Oh, just kidding. I do talk about them more. So now some examples. So sort of what our results were. We found that they were really good at matching semantics. So now, as a different example, we're going to use the sentence, in 2017, we lost $500 billion in trade with China, which I believe is also from the State of the Union. So this method is very good, specifically the NLP one, at saying, you know, last year in 2017, or 500 billion, $500 billion, at identifying that these are very similar. And it's even good when we have different sentence structures. So now trade deficit is replaced with lost in trade, which is sort of scattered throughout the sentence. But again, we see that our models sort of do this sort of thing very well. Where they have a lot more trouble is when there are a lot of similar words, but the sentences differ on a really important word for meaning. And this is sort of what we try to avoid by using the weighting, but we couldn't get around it completely. So here, last year we lost 500 billion in trade with China, and we've lost 500 factories since 2017 due to trade with China. If you replaced factories with billion, these sentences would be paraphrases. But because one is talking about, you know, how much money we lost and how many factories were shut down, we really don't want to be matching these sentences. And this is the sort of thing that fooled our models. Yes.
So another question, did you just, a sentence has like different subject and objects, like with the original kind, does it give the same result? Like, is it considered a match or not?
So it depends on how similar they are.
No, I mean, like, for example, makes it or a kind mixture.
So we don't take word order into account. We just take part of speech, which is very common in a lot of NLP. It's a common criticism of a lot of bag of words models. Yeah, so we
this
don't
is
take,
for the support vector machine approach, right? But for the other neural network based, it would.
Yeah. Okay. So in analyzing how our models did, we realized that we were being too narrow in our approach. So if we look back at the original fact check, this isn't a paraphrase of what Trump originally said, right? One is saying 2.4 million new jobs and one is saying 1.8, right? So we really built our models to not return this. And sometimes it did return this just because of the problem where if you just switch one word, it tends to get messed up. But we built our models to not return this. Additionally, if he had said we created more than 1 million new jobs, then this is still a relevant fact check. But now this is very much not a paraphrase, right? If I say we've created more than 1 million new jobs and asked you, have we created 1.8 million? You wouldn't know. It could be 1.8, but it could be 2.4. It could be 3.6. So we went back to the drawing board. This was like 5 weeks into the summer, so it took us like half the summer to realize this, but also we had half the summer left, so it could have been worse. So before, we were looking at paraphrases, when once X implies Y and Y implies X. But now we also want to look at contradiction, when X implies that Y must be false and Y implies that X must be false. So the original example was a contradiction. But also, we want to be looking at entailment, and paraphrase is a subset of entailment, which is when one sentence implies the other. So that's this example. What Trump said, what the Washington Post statistic implied what Trump said, but not the other way around. Yes. And specifically, we care if something in our database entails something that, for example, Trump said, but we don't care if what Trump said implies something in the database. So we want this to be one-sided, whereas paraphrase is symmetric.
And just to make things even more complicated, some of the statements in our database are not stated in a positive fashion, right?
Yes.
It could be that certain things are not true.
Yes.
So
Okay, so yes, our problem gets significantly harder once we realize this. And we can say maybe our previous methods do entailment well, but it turns out that that's just not true. Essentially, they don't perform well under entailment. So we need something new. So first, we find this data set. It has 433,000 sentence pairs, which are labeled from 9 genres. It's short for multi-genre natural language inference data set. This is actually a well-studied problem in NLP of identifying contradictions, entailments, and neutral, which is neither contradiction nor entailment, and which is why this data set exists. So here are some examples, and these are across a few of the genres. We're particularly interested in telephone speech because it sounds a lot like what we're going to get out of speech to text. But you can also sort of see here how this is a really hard problem. Yeah. But also having so many sentence pairs greatly increase the or opens up new doors because the more data you have, the better your models are going to do, and you can also use neural networks. So our final and best approach, during the summer, organization called OpenAI published a paper in which they beat the state of the art. So they have a new best score on 12 out of 15 well-known NLP challenges, including multi-NLI, which is the one we care about. And luckily, they published their weights and some of their code, which meant that we could recreate their results, or nearly recreate them, without having to spend as much time training and developing the model, which is amazing. So going into their model a little bit, there are really 2 things that make it above and beyond what was there before. So first, it uses a transformer architecture. So one thing really difficult in neural networks is neural networks applied to the English language is what I talked about before, in that words reference words earlier in the sentence. So for example, in this example on the right, the animal didn't cross the street because it was too tired. Here we see that the word it is referring to the animal earlier in the sentence. But it's very hard for a neural network to realize that. So there are a few common approaches to solve this, one being RNNs, CNNs, and LSTMs. Those are the main 3. But the transformer was just published in December by Google AI, and it basically improves on those 3. How does it do it? Don't really know. But we vaguely know. But we don't we didn't go too much into the specifics.
we can read that paper.
Yeah,
Right.
yeah, you should read the paper. But sort of empirically, what it does really well is identify what it is referring to. So in the second example, the animal didn't cross the street because it was too wide. We sort of know that it in this sentence refers to street rather than animal. However, between these 2 sentences, the only thing that changed was the last word, right? From tired to wide, suddenly it refers to animal in the first and street in the second. And the transformer does a really good job of identifying this. The coloring here is essentially what the transformer does is it gives a score for each word as a weighted sum of the scores for all the other words in the sentence. And here we're looking at the weights. So darker blue means more heavily weighted. So in the first sentence, animal is a lot more heavily weighted than street. And in the second sentence, it's the reverse. So essentially, the transformer does a really good job of identifying sentence structure in English and identifying what words are referring to. The second thing that this model does really well is it's semi-supervised learning. So what that means is supervised learning is when you have training data and you use that training data to sort of extrapolate to new data. Unsupervised is when you're sort of trying to identify patterns in unlabeled data. So this uses both. So the big problem with supervised learning is it requires tons and tons of training examples, and that's usually what limits it. So what they did is they said we only have 433,000 NLI examples, or only so many paraphrase matching examples, but we have tons and tons of free text. So they went to a corpus of books, which includes, I think, like over 1 billion words of free text. And they trained their model. It took them a month on an incredibly powerful computer, essentially to, if I give you 15 words, can you predict the next word? And what this does is it gives the model sort of like a general understanding of the English language. And these books are across genres, which helps. So, and then once they have these model weights, and their model has something like 80,000 parameters, I want to say, but don't quote me on that, then they more specifically train it on the problem at hand. And specifically, after they did this initial unsupervised training step, they trained it on 15 different smaller data sets, which are the NLP challenges. And so this model was able to do really, really well on a variety of challenges, including, like, for example, sentiment analysis, which isn't at all related to natural language inference. But using the same base model, they were able to do well on both, which is really, really impressive. Because in a lot of these competitions, people tailor their model to the specific problem. This is an extremely general model that like blows them all away. So anyway, yes. Any questions on that? Yes. Yeah, so it's a transformer model, which is a really recent type of neural network. Yeah. Is that what you mean?
So there is a pointer that we put in the README file under the claim matching.
Yeah.
I think in one of those meetings, maybe some of you could present that paper and explain to the rest of us how exactly they do that. I think that'll be a useful exercise, especially when we have identify subgroups who are working on that specific problem. And I think it's important to understand exactly where we're getting improvements from.
Yeah.
Yeah.
Where is that file?
So if you go look under the shared the folder, there is a directory called claim matching.
README.
Yeah, it's going to the README. Did I get the pointer right? Actually, I haven't.
Oh, I haven't looked.
Yeah,
I can check.
The NIPS paper.
This is a Google
The
paper.
transformer.
Yeah, the Google
model,
paper is the one about transformer, and there's
Yeah.
some. I couldn't find the exact pointer for the OpenAI stuff.
Yeah,
but
I
they-
checked your OpenAI pointer. That's
Okay,
right.
so that's right.
So yeah, pretty much everything that we know about this model is either from reading the code or reading the transformer model or reading OpenAI's paper. But yeah.
It's the one that about like for identify it, what does it refer to? Which one is that?
That's the transformer model.
Oh, that is also that one.
So the transformer model talks about why the transformer is good, and the OpenAI one is a lot about why semi-supervised learning is really powerful. Yeah. So now our results. So we essentially, they published their code on GitHub with the model weights from that 30 days of training on the book corpus, which meant that we didn't have to do that over again, which was good because there are only like 10 days of the program left. But what it meant is we could do the supervised step where we retrained it on the multi-NLI data set. So our results, we did both multi-class classification and binary. So multi-class is when we distinguish between contradiction and entailment. And in binary, we combine those categories because when we're returning fact checks, we don't really care if we're returning it because of contradiction or entailment. So we can combine them and get slightly better results. But what we find is this is based on the multi-NLI test data set. So we train on some data, then we tune our hyperparameters on a dev set, and then test it on examples we've never seen before. We get 81.6% accuracy, which is, and the state of the art that OpenAI got was 82.1%. So we're extremely, extremely close.
Right. So one of those metrics is not doing as well as the other, right? So if you have a neutral, then we tend to, wait, so the true value is neutral, but we actually say, oh, it's entailment or a contradiction.
Yeah.
More often. So sort of the precision is not as good as the recall.
Yeah, and these, we trained it to do as well as possible on MNLI, but it's possible that you want to sort of train it with a different objective function. If you find that it's returning too many false positives, false positives, then you can use a different objective function to achieve that goal.
Right, right. But this is test on the standard corpus.
Yes.
Right.
And we did that so that we could compare to other people's results.
Do we have the results for, I guess we don't really have a huge test set, but do you have some intuition as to, when this is applied in our setting, how well it does?
Not really, because the data set we made is only paraphrase.
That's true, right?
Which is,
so we don't have ground truth even.
Yeah. And that's just because we ran out of time. But that's obviously something that would be important to do, test on specifically political sentiment.
That's why I would pushing you guys to really look at the data harnessing part, because this is very important for both training and also evaluation of all these techniques. We need more data basically just to test whether we're doing well or not.
And ideally, that could be added, or it could be, rather than starting from scratch with the training, you could use the previous weights from the MNLI data set. So book corpus, MNLI, very specific data set.
Yeah, so you said you got the weights already and then train all the political sentence on that. So did you just initialize all the weights using the one they publish and then keep training, or how did that part work?
So neural networks use gradient descent, which finds local minima, but not necessarily global minima. So first they trained on the book, and then rather than starting with random weights, which is what you normally do, you start with those weights and start your gradient descent there, and hopefully that gets you closer to a global minima.
Yeah, so you use the political sentence, the data set that you got to keep going from there.
No, that's what we would ideally like to do, but our data set is only paraphrase, so we couldn't do that. Essentially, we didn't have a political data set to use.
Oh, so you're basically just using the weights that they published.
We trained it on the MNLI data set because they didn't publish the MNLI specific weights. They just published after the unsupervised step.
So we need to basically come up with our analogy to that data set.
Yeah.
That is large enough, maybe targeting political domains or whatever we want to targeting, and then train it on there and test. That would be the right way to evaluate it.
Yeah.
And MMLI usually has multiple domains, right?
Yes, it's from 9 different genres. And they're very different, right? Like telephone speech is very different than the government's report after 9/11. So it's a wide variety of language.
So do they have a politics domain? Or?
Not really. They have some which, 9/11 report is somewhat political, but it's very different than how politicians speak, right, on TV. Uh-oh. Hopefully it will be
My
fine.
battery or your battery?
Oh. It looks like my battery,
Okay.
but I think it will be okay.
All right.
I think it's pretty close to me. Okay. Oh, yeah. So then we find that we do a little bit better if we combine the entailment and contradiction categories, but not all that much better, which is because if you look at the left confusion matrix, we don't often confuse entailment with contradiction. We're much more likely to think something is neutral when it's entailment or neutral when it's contradiction. Okay, so now this is sort of a demo. We built a very, very simple Flask front end. This is putting in the text of the State of the Union. And you can just sort of see it finds a few fact checks. But yeah, it gives a confidence score also. So that's nice. But yeah, this is just a very simple front end, not at all ready to display to anyone.
But this is actually happening in quote unquote pseudo real time, in the sense that it's you have the transcript up front, but you're actually in real time going through every sentence and applying that entire pipeline of algorithms, except the speech to text.
Yes.
Right. And this is using
the NLP model.
NLP one.
This was before we had the
vector machine one. Right.
Which is the fastest one.
Right. So how slow are the other ones? That's the other.
So the transformer model is really slow, but so essentially we couldn't run it on our computers because it would take like 4 hours to do one example, and part of that is
one
because,
example.
Yes, because
one
for
pair.
No. One
sentence.
Because
one sentence.
every sentence we're looking through many database sentences, comparing it to many database sentences. So it ends up being something, some thousands of comparisons just for one sentence. So if each one takes a long time, the whole process takes even longer. So one thing that might be good to try is somehow limiting the number of sentences you check about, either by like recent sentences or some topic model. But if you use a better VM with some GPUs, then we can get it down to, I think we got it down to like 4 minutes with not that powerful of a VM
Per sentence. Right.
Yeah.
So
it's like,
yeah. So you could imagine, I mean, a brute force way of doing this would be you basically pipeline processing. You have like a bunch of machines, each looking at the sentence in a round-robin fashion, and you have a 4-minute delay, but throughput will be able to sustain the speech, the speed of the speech.
yeah.
How was the neural network implemented on? What system did you use?
What do you mean?
So this you're talking about evaluation on this MNLab
Yeah.
data, right? It's developed by OpenAI.
The MNLI dataset is a publicly available dataset from NYU.
Sure, but the transformer model that you used, is that a third-party application, or did you have to code it yourself?
We found OpenAI published their code on their GitHub repository.
OpenAI.
Yeah.
Right. And so is it is it coded in some, what is it?
It's in
Python
Python.
code?
Yeah. It's in Python. And it uses
you're running on a single server?
Yes, but it uses GPUs. So it's with TensorFlow for GPUs. So I think we were running it on maybe 2 or 4 or something like that. Yeah, and GPUs are a lot more powerful than the CPU.
Yeah. And one direction could be TensorFlow APIs are available in Spark, that is distributed computing.
Yeah.
So we could port it on that, see if it can distribute it well.
Right. Well, there's 2 parts, right? One is kind of just you take a pair of sentences and run through this model, and you can figure out ways how to speed that up. But there's also the aspect of we're doing this for every single sentence in the database, which is not sort of this requires some more algorithmic innovation there to speed up.
That needs research.
Right.
And that's something we didn't really touch.
Yeah. So I mean, there are ways to kind of, for example, you can train a simpler model that makes faster predictions, maybe with a different, utility function that maybe penalizes more false. One of those things, right? You just do the first pass. Yeah. So there are. This is what the infrastructure team needs to work on, how to make these things actually up, fast and speedy. So.
Yeah, so that's pretty much what we did. This is sort of what we envisioned from our future work at the end, from our final presentation. First, making a political NLI data set like we already sort of talked about, so that you could get even more specific than an improved or really like any user interface. Ours was very much thrown together. And then obviously like this model hadn't been published when we started at the beginning of the summer. They're going to be continual improvements, so continuing to update the model. I think that is it. Yeah. Yeah.
Do you do like any accounting for like outdated data? So like you said they're like when they did the fact check in the past, like 1.8 might have been the real figure, but maybe since then it's gone to 2.4.
Yeah, it's not, and that's a very good point. Lots of them will say like last year.
Yeah.
And we have when each fact check was published, so it would be possible to map those to specific years. But we aren't doing that at all. We're sort of, yeah, which is bad, but yeah. And that's another thing where limiting to more recent fact checks might help that probably.
Right, so this could help both in terms of performance and indeed accuracy. Yeah, so what are the ways, I mean, the other interesting possibility is to look beyond just the sentence, features from the sentences, right?
Yeah.
And I'm curious as to how this can be combined with, say, for example, OpenAI's transformer-based models, right? So if I have additional features derived from other contextual information, like time, for example, that's very specific, and I'm not sure how it works in conjunction with a neural network-based model, right? So one is kind of more like this fudge of black box stuff, and then the other one is something that I have much higher confidence in what it is about. It will be interesting to look at how we can incorporate these other signals in some way.
And we don't use anything from the fact check itself. So each of these sentences are associated with an article where they write about, the subject, but we're not touching it at all.
Right. I guess another high-level question is whether we're going after this level of precision in terms of entailment, and because of all the other issues, right? We can do a very, very good job in telling whether something implies another, but then because we're missing some contextual signals, we could be getting the wrong verdict in some way. I mean, the other option is just simply to say, relax, we're not going to tell you the verdict, but just to surface the related fact checks.
Yeah. And part of that problem is that a lot of the sentences in the database are false, right? So if a fact check, if Washington Post says what Donald Trump said was entirely false, we get the false statement usually, which means that we can't necessarily interpret the truth value, only say that it's related. So something we talked about that we would like to see is sort of a true statement that is the heart of each fact check and share the facts.
I mean, if we have a perfect model, one could say that we simply just take that statement and just negate it. Like, it is not true that blah, 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 and you just fit it in there. But somehow I doubt this will.
Yeah, no, I don't think that it's that good.
That might be, Yeah, so there are lots of still open challenges, and we'll have to basically, overcome these obstacles one by one. But thanks to Ethan and the rest of the Data Plus team, now we have a pretty good picture of what's ahead of us. So you're not starting from completely blank slate. So there's a lot of insight already we have, and code. And these guys have volunteered, quote unquote, themselves to help. So if we have any questions about, code or even just to brainstorm potential new directions, they're here to help. Yes. So great. Thanks a lot, Ethan. Any other questions for Ethan?
Is the GitLab the code that you have?
Yeah, all of our code is in the GitLab.
How do they get access to it?
That's my responsibility.
Oh.
I still need to make a pass and make sure that every one of you
sign into gitlab.oit.duke.edu at least once, so I can find you there to add you. If you do not sign up, I cannot find you there. And I'll do this, tonight. So try to do this right after the meeting, before the power goes out.
And we have lots of readmes in the code, which has more information.
Great. Great. So we have 10 more minutes left. So I want to take that time to maybe go over, your interests a little bit, and maybe talk about how to divide up into the smaller teams. But Ethan, you're free to
Thank you.
seek shelter.
Yes.
So all the sentences that you check against are from the MLI database? Or?
So when we were getting those accuracy scores, that was trained and tested on MNLI data.
Yeah.
But when we're sort of like running it through the pipeline, such as in the demo, even though it wasn't that model, that would be on sentences from Share the Facts. So we're comparing a sentence that was spoken to a sentence in Share the Facts.
But the model was not trained from those data.
Correct. It's still trained from MNLI.
Oh.
Yeah. And that's because the Share the Facts isn't like labeled data.
Oh, it's not?
No. It's just sentences and associated fact checks.
Right. So the way we set up the problem is for our purposes, label data basically consists of a pair of sentences, and you say whether it's a match or not. But more generally, for entailment type of processing, you would need to say for this pair, what exactly is the direction of entailment, right? So we need to come up with that kind of data. What's inside Share the Facts database is, for instance, only one of those things, one component of that pair. Now that component is further annotated with true or false, and in some cases like half true, and 3 Pinocchios and stuff like that. So it's very difficult to convert them into truth values. And that's some other challenge we have to deal with.
Yeah. So our model doesn't say anything like what Trump just said is true or what he just said is false. It just says, here's something related that you might want to check out.
So basically it compares with all the sentences in the database and return the one that if there's contradiction or entailment.
Yeah, that's right. That's right. Cool.
Thank you guys. Good
Great.
luck.
Thanks a lot. All right. So we have less than 10 minutes to get organized a little bit. But the nice thing is that the next meeting will be on Monday. So we almost get to, in a sense, continue this discussion. But I want to just go back to okay. Go back to this project idea document, and this is where you have signed in with your interests. So let me try to share the screen, if I can figure out how. So I'm going to share the application window. Okay, should I just do entire screen? Actually, I'm not sure what I'm doing.
I think if you do entire screen.
Okay, let's do application window. Okay, this is better. Right. Okay, cool. Now we can look at that. So I just briefly going over these, right? So claim matching, I think after this discussion led by Ethan, it should be very clear what the claim matching component is trying to address. But let me just maybe reiterate a little bit about this part about human harnessing and media matching. So human harnessing, I think a big component of it is trying to essentially build up this data set for evaluation and training for claim matching in some sense. And we've realized that throughout the course of Data Plus project, it's very difficult to collect this data. Yeah.
Do you use like Amazon mTurk or?
We could use mTurk, but we have to design it correctly. So in a sense, what they did was like Mechanical Turk, free Mechanical Turk using Duke Plus, Data Plus, summary in terms. right?
Oh yeah.
But what they found out is that people just did not paraphrase things aggressively enough, and they end up with very simple training examples where it's very easy for algorithm to detect whether something is correct or not. Now, this may or may not be an issue, I think, in practice, right? Because a lot of times in politics, politicians will repeat the same exact talking points. So maybe this is what you get. They will not paraphrase it too much, but it's hard to say. I mean, there are cases where we've had examples where the paraphrasing is very, very, I would say, aggressive, and then our algorithm will just fail miserably on that. It would be nice to capture some of these cases. But if you simply ask people to come up with paraphrases of the same statement, they are not creative enough, quote unquote.
Yeah.
So how to do this is not completely clear. So we need to, I mean, we had all kinds of ideas about how to do this, right? There's also examples where you take some sentence, you translate it using Google Translate, and you just Bing translate it into another language, and back and forth, and eventually get some other representation of the same sentence, in hope that there will be a good paraphrase. But I think in those cases, also be simple cases. There are some very, very nasty examples. If you go back to the Slack channel and go back and see, we had some discussion of those. Like, it's just no way. It will be nice to have some examples like that in the test data set. So how to collect that is not even clear. And secondly, what's important here is that, as you can see, it's very easy to get things that are not exact matches, and it will be pretty dangerous when we're public facing and we're pushing out these tweets and saying somebody's lying because we found this match, and then you realize, oh, there's some nuance in the way these things are stated. So there needs to be some human curation in the loop before it hits the mass market, right? So what we envision is something like there will be a group of editors who's watching this live event, and our tool will be presenting the string of things, fact checks we found to them. So it's very easy for them to sort through what's relevant, what's interesting, and then maybe ask them to select in real time what are the things that can be safely pushed out to the public. And then with the public-facing app would take that stream that's sanitized by the editors. So, but if you think about it, it's this requires some design of how to make this work, and also how to use the data you collected as a result to feed back to training and evaluation. So you could imagine that this group of editors sitting in the room for this live event, they're doing this for the purpose of pushing something out to the public. But after this is done, the dust settles, their annotation becomes very valuable training data to improve our algorithms in the next round, right? So this entire ecosystem has to be set up. So this is where I think sort of where I'm trying to get at, what I'm trying to get at in terms of human harnessing. And this is pretty challenging because you have to think about, what are the right ways to bring in the human aspect into this picture. It's not trivial at all. It will require some innovative thinking and so on. And media matching is basically a way of scaling up, as we talked about last time, because it's very difficult, as you can tell, right? If you're simply brute force, using brute force to match every single incoming sentence with the database of all the fact checks, that's going to take a long time. You cannot afford to do this for every single viewer of this live event. What really happens is there needs to be a backend view, backend processing that does this once for this one media event, and then when users tune in to this media event, we just need to know that this person is watching that event. So there's a nice little problem of how do you actually just detect the audio signature and match it to the right event? That's kind of like a standalone problem, but I think it's a very, very interesting one. But now I realize, after going through this, maybe what we can do, so I know a lot of people are interested in the first component, claim matching, partly because it's more well-defined problem. Data Plus team have worked a lot on that. But media matching and human harnessing, at least media matching is well-defined. Human harnessing is a little less well-defined. You have to figure out what's the best way to do it. So I'm thinking about just merging these two into like one task force, if you will. because in some sense, it's kind of dealing with human interaction in some way. Because media matching is also in support of end user using our services. So I'm thinking about just combining these two into one group. And then, of course, there's the infrastructure group, which I think needs to be responsible for policing the code and enforcing the APIs and different components and scaling it up, scaling the whole system up. So I do have a proposal of how to divide you guys up based on your input. Maybe I can share that with you and see if you like that division of labor. Let me fire up QuickTime. And let me try to share the screen, switch the screen over there. We're almost out of time, so maybe what I can do is just come on. Oh, okay, it works. Let me go back here and screen share differently. Application window and this. Okay. All right. So here is the claim matching team. So I'm basically putting Yuhao, who's absent, as sort of the grad liaison or grad project manager in some sense, and then Bingbo. Good. And Fan. Connie. And Jason. All right. And Jason is remote. So we'll see how much time he will be able to spend on this effort. But then with media matching, plus the human harnessing, again, we need a better name. So I think the first task for the team is to basically come up with a very, very nice team name. For example, MMHH. So Yuhao, I'm basically putting him here too. So I'm thinking about here. Is that the right way to?
Yeah. Yep.
Great. You were not here in the last meeting. Right?
I was not.
Yeah. So maybe you can also give a brief intro to the rest of us.
Yeah. My name is Tokir Aziz. I'm a master's student finishing up my degree in bioethics and science policy. And I wasn't here last time because I was doing like a photojournalism project in refugee camps in Salem, Bangladesh.
So welcome aboard. And Jerry? All right. Matt? Good. Okay. Archana is not here, but I'm putting her up. All right. Okay, so that's team of 4 also here. And then infrastructure team. So I'm thinking putting Mayuresh as the project manager and Liu Yi, Harry, all right, and Scott. All right. Wait, Scott, you were not here last week. Yeah, so you want to give
the meeting was in between classes because I had 2 classes on Mondays in the morning. Yeah, so okay, I'm Scott. I'm a sophomore. I'm studying comp sci and Navy statistics, and I'm taking professor's class in 316 this semester. So it got me interested in like data in databases. So I searched him up and I emailed him when I could participate in his project, and he graciously said yes. So,
All right, so this is what we have. Are you guys happy with the assignment? Okay, good. That was easy. I thought we were going to spend like half of the meeting discussing this. Of course, this is tentative. As things evolve, we'll figure out, how the scopes of these projects
Is this
overlap
all
and
the
so on.
people or other people unassigned?
So yeah, so I'm missing still several people, but I do not know at this point how much time they can commit. So we'll start with this assumption, and people can join in. Yeah, so first order business is that I think, weekly meeting is not just one time. The whole group is probably not going to be very productive once we have more concrete tasks. So I will ask you guys, once you have this teams, each team to figure out another time that you can meet during the week. So at least we're meeting twice a week. One time in a smaller group, the other time with a larger team. And as I said, this room is going to be reserved on both time slots. So we actually have this room every week, even though we're meeting every other week in the slot. So that's one. So work out a regular meeting slot, and I'll try to make them as well in some of the meetings. So I'll probably jump around in different project groups. And there's also a number of, I think, immediate to-dos to really get started for these teams. So I'm thinking about, for the infrastructure team, we should start really by studying, what code is out there developed by Data Plus, and try to figure out maybe a way to carve them out into, components. And this also relates to what Harry suggested in the doc, right? So basically building an, what was the phrase again? Omnipresent.
Chrome extension, basically.
Yeah. So that would be a perfect example.
What I suggested, but I was.
Oh, this was not okay. Who suggested that? Yeah. Okay. Okay. So mysterious person suggested this idea, but now, but that's actually one example where you have to design your infrastructure in a way, and your system in a way that you can easily plug in another service that serves a different platform, but essentially leveraging the same technology. So I think bearing that in mind, those kind of extensions would be something that the infrastructure team also look into. So I'm hoping that soon the infrastructure team will be able to kind of do a high-level walkthrough of the code with the rest of the group, and then propose some architecture design there. And then for the other team, for the media matching and human harnessing team, I think some of the immediate tasks could be to look at speech-to-text conversion right now, because speech-to-text conversion right now will give us some insight in terms of media matching as well, which is the job of figuring out when you're listening to something, how do you know you're listening to this media stream versus the other one? And also some of the data annotation code, code for collecting training set or evaluation set, test set, that Data Plus team has already done, and you can probably make a pass over it and see, what are the points to improve on and how to make it more scalable. Maybe Mechanical Turk, but how to design these tasks in a better way so that we can solicit more useful feedback from the user. And then for the claim matching team, I think the very first thing to do is to really go through all the prior arts and code, and try to understand them first of all, but also working with the media matching and human harnessing team to come up with basically some data set with which we can actually start evaluating these different approaches. So that's kind of like the high level, assignments. All right. Yeah.
So do we not find any data set that has two similar sentences or two contradicting sentences? So there's no.
We do have something along this line.
So is it online?
It is online. I'll have to look more closely. So I know one place where we store that data set, but you should just ask the question on Slack, because once we have access, I've given everybody access to the GitLab, then the Data Plus team should be able to point you to the specific data sets that they've used for this purpose.
So there will be more data to play with. But bear in mind that's not enough. We need to expand on that data set. Okay, so that's what I have. Yeah, hopefully Mayuresh will have the meeting minutes soon, and I'll type up some of this stuff as well. So, all right, so that's it, and I'll see you guys on Monday. And if you have any ideas for agenda items on Monday, I realize it's now, already Wednesday. So, and what you guys want to talk about, let me know. If not, I'll come up with something. Okay. All right. Okay, thanks a lot. So I'm gonna stop sharing here, and I think that's about it for the meeting. So I'll stop the recording as well. Bye-bye.